In Lecture 1 of this module, we want to introduce the very important concept of intermolecular forces. Now recall from first semester general chemistry that a molecule like HCl would be polar due to its single polar covalent bond, this HCl bond here, and because of the linear shape of the molecule. Now in the cartoon to the right, the delta plus, these are small Greek delta plus and delta minus symbols, represent partial positive and partial negative ends of the HCl molecule, which is a way of representing the polar nature of the molecule. Now the HCl molecule has this particular shape here because, of course, a chlorine atom is larger than a hydrogen atom. So we say the molecule is linear, meaning it's shaped like a straight line in line with this HCl bond, but in what's called this space-filling model, the molecule doesn't look perfectly symmetrical because chlorine is larger than hydrogen. In any event, HCl is a polar bond, something hopefully you recall from General Chemistry 1, and because of that, the entire molecule is polar, and so we have a partially positive and a partially negative end of the molecule. Under standard conditions, and remember standard conditions means 1 atmosphere of pressure, usually at 25 degrees C, HCl is actually in the gas phase, and there are relatively long distances between HCl molecules. However, under conditions of high pressure and low temperature, HCl can be condensed into a liquid. I have a little footnote here because I want you to keep in mind that the liquid HCl that you see in a general chemistry laboratory is really not pure liquid HCl. It's actually HCl gas bubbled into water to form an aqueous solution of HCl. In any event, if we did condense HCl into a liquid, the distances between HCl molecules would become much smaller, and we could represent two random HCl molecules near each other in the liquid state as shown below in this diagram here. At this point, it's important to distinguish between intramolecular forces. An intramolecular force, that would be forces within a molecule, would here be the HCl covalent bonds, which are very strong bonds holding each HCl molecule together. Those are intramolecular forces. We want to distinguish those from the weaker but still very important in the topic of this lecture, intermolecular forces between HCl molecules, represented by these red hash marks. And these intermolecular forces cause the HCl molecules to be more favorably disposed to be near each other with the hydrogen end of one molecule pointed toward the chlorine end of the other. Because remember, these are both polar molecules with a partially positive and partially negative end in each molecule, so it makes sense that if they're near each other, they would be predisposed to line up so that the partially positive end of one is closer to the partially negative end of the other, and that force of attraction between those molecules is called an intermolecular force. We can put some numbers on the intra and intermolecular forces in HCl molecules. The bond energy of a single HCl covalent bond is 431 kilojoules per mole. Now that number may or may not mean anything to you, but let's compare it to another number, and the other number would be the heat of vaporization of HCl liquid, which has been measured to be 16 kilojoules per mole. Obviously 16 is much less than 431. So what's the point here? Well, the bond energy, the HCl bond energy, is representative of the intramolecular force holding each HCl molecule together, since it represents the energy needed to actually break the HCl bonds, to separate each molecule into hydrogen and chlorine atoms. However, so that's a measure of the intramolecular force holding each molecule together. The delta H of vaporization, sometimes called the enthalpy of vaporization, represents the energy needed to separate two whole HCl molecules in the liquid form into the gas form, where there's larger spaces between the molecules. So this delta H of vaporization is a measure of the intermolecular force between these two HCl molecules, since it represents the amount of energy necessary to separate these two molecules in the liquid state and form the gas. We will spend some time categorizing various types of intermolecular forces. In addition, we will examine what factors contribute to larger or smaller intermolecular forces, and how the magnitude or size of these intermolecular forces are reflected in observable macroscopic properties, meaning things that we can observe, such as boiling points, delta H of vaporization values, and even what phase a substance exists in under standard conditions. Before we formally categorize these various types of intermolecular forces, which we'll start to do on the next slide, let's look at an example of how a macroscopic property, in this case, the phase of a substance under standard conditions, meaning whether that substance exists as a solid, liquid, or gas under standard conditions, how that property can be correlated to the magnitude of intermolecular forces operating between molecules of that substance. Now, I've thrown a lot of information up on the slide all at once. What we have here are representations of chlorine, bromine, and iodine molecules. These are all nonpolar molecules, meaning they don't have a partially positive or partially negative end. And the only intermolecular forces operating here are called dispersion forces. We'll talk more about dispersion forces soon, but for now we'll remember that nonpolar molecules, of which chlorine, bromine, and iodine are nonpolar molecules, their intermolecular forces are called dispersion forces. These types of intermolecular forces, the dispersion forces, tend to increase with increasing molar mass and increasing size of the molecules. Let's look at the representations of these molecules. Here's the formula for a chlorine molecule. Here's its molar mass. Formula for bromine and iodine molecules. You can see bromine has a larger molar mass than chlorine. Iodine has the largest molar mass. I've tried to draw space-filling models of the chlorine molecule and the bromine molecule and the iodine molecule. There's a single covalent bond holding each of these together. This row here, the XX bond distance, is just a measure of the distance in what's called picometers between the center of one chlorine atom and the center of the other, or the center of one bromine atom and the center of the other. So you can see that the molecules not only are becoming heavier, going from chlorine to bromine to iodine, they're becoming larger because the bond distance here is getting bigger in each one. If you look at the pictures below, you can see that chlorine, which is the smallest and lightest molecule, exists as a gas under standard conditions. And that's represented here, chlorine gas, large distances between the chlorine molecules. Bromine, however, exists as a liquid under standard conditions at room temperature. And you can see the bromine molecules are much closer together in the liquid. And iodine, under the same conditions, exists as a solid. So we have iodine molecules packed very closely together in a solid. So you can see at room temperature and 1 atmosphere of pressure, chlorine, which is the lightest and smallest molecule, exists as a gas. Bromine is a liquid. Iodine, heaviest and largest molecule, exists as a solid. And this is a reflection of the intermolecular forces operating between these. In other words, chlorine exhibits the weakest dispersion forces, weakest intermolecular forces. So it exists as a gas at room temperature. Iodine exhibits the largest dispersion forces or intermolecular forces because it's heaviest and largest, and it exists as a solid at room temperature. Interestingly, despite the fact that iodine has sufficiently large intermolecular forces to allow it to exist as a solid at room temperature, if you take some, put it in a flask, and hold the bottom of the flask with your hand, the little bit of heat from your hand will easily sublime the solid iodine. In other words, it'll take it actually directly from a solid to a gas, because although it does have the largest intermolecular forces of the 3 molecules here, the intermolecular forces in iodine are really not all that large, so it's fairly easy to sublime. You'll also notice the pictures here make it look like the iodine solid is a different color, and it's not. A closer representation of the real color of iodine is actually in this picture of the flask here and not in this cartoon. So we're now ready to introduce the various types of intermolecular forces. On the last slide, we introduced one, dispersion forces. We'll talk about that, but we'll introduce some others. So the first main type of intermolecular force are dispersion forces, and all molecules, both polar and nonpolar, display these types of intermolecular attractions. Dispersion forces are also sometimes referred to as London dispersion forces. For nonpolar molecules, such as the 3 molecules shown on the previous slide, dispersion forces are the only intermolecular forces in play. The second type of intermolecular force we'll discuss are dipole-dipole forces. Surprise, surprise, they're displayed by polar molecules. We previously discussed the intermolecular forces between molecules of HCl. We did that on the first slide. Now, since each HCl molecule is polar, in other words, each molecule is considered a dipole with partially positive and partially negative charges on opposite ends of the molecule. Dipole means it has 2 different charges on 2 ends of the molecule. The intermolecular forces at play in HCl would be considered dipole-dipole forces. Keep in mind that there would also be dispersion forces operating between HCl molecules because all molecules, whether polar or nonpolar, display dispersion forces. A third type of intermolecular force we'll discuss in this lecture is called hydrogen bonding. This is not an actual bond in the sense of being compared to an actual single, double, or triple covalent bond in a molecule. but rather it's a special type of dipole-dipole force centered around hydrogen atoms bonded to very electronegative atoms such as nitrogen, oxygen, and fluorine. Water is the typical example used to illustrate hydrogen bonding. You can see the hash marks in the graphic up in the upper right of these slides where we have two water molecules and they seem to have some sort of attraction for each other, and here we're showing hydrogen bonding. You see these hash marks. Hydrogen attached to oxygen on the one water molecule, having some sort of special attraction for oxygen on the other water molecule. And hydrogen bonding in water and in other molecules can have a great effect on their behaviors. We'll talk more about that soon. Finally, the last intermolecular force we'll describe are called ion-dipole forces, and this is obviously an attraction between a polar molecule, a dipole, and an ion. This type of intermolecular force is primarily responsible for the solubility of many ionic compounds, such as sodium chloride, in water. In the following slides, we will consider each type of intermolecular force in turn. Keep in mind, however, that many real molecules show a combination of intermolecular forces, not just one of these types, but maybe several. And when a molecule has several intermolecular forces in play, one type of intermolecular force might dominate over the others, and we'll try to make judgments about that. So let's start talking in more detail about dispersion forces, which we introduced when we talked about chlorine, bromine, and iodine. Now remember, all molecules, both polar and nonpolar, display these types of intermolecular attractions. In the previous slide, when we dealt with chlorine, bromine, and iodine, we were specifically talking about dispersion forces. But we want to illustrate now dispersion forces in a more fundamental way. So we're going to start with an even simpler example, two helium atoms represented as spheres. Again, I threw a lot of information up on the slide all at once, but we can make our way through this. And the point here is to try to convince you how dispersion forces could arise between molecules. Because you might ask, if there's in a nonpolar molecule like chlorine, bromine, and iodine, if there are no partially positive and partially negative ends of those molecules, how would they be attracted to each other at all? So we're going to try to explain how dispersion force could arise. And we'll use two helium atoms as an example. So here's the general idea. Suppose two helium atoms, by chance, are near each other, and that's supposed to be depicted in column A. There's two descriptions of the helium atoms in column A. In the top cartoon, we have the two helium atoms. The dark dots are the nuclei of the helium atoms. Remember, helium atoms only have 2 electrons each. And in this cartoon, remember, electrons are randomly distributed in what could be called an electron cloud. And we're going to say that if we took a snapshot picture, that the 2 electrons in this helium atom are here and here at that instant, and 2 electrons for this helium atom are here and here. And if we just take a purely electron cloud view, we'd say the electrons are evenly distributed around each nucleus. But here we're claiming we could take a snapshot and see where they were at any instant. Now, suppose, again, by chance, that one of the helium atoms has an unsymmetrical distribution of electrons, and so for a split second looks polar. In other words, it forms a temporary dipole. Let me explain. Let's suppose we have our two helium atoms next to each other. This helium atom has the two electrons in our snapshot fairly evenly distributed from each other, but this helium atom here, just for a split second, has two electrons that are closer to each other and on one side of the nucleus. That would mean that in this particular helium atom, there's an unsymmetrical distribution of negative charge, and so we'd say there's a little partial negative charge on one end of the molecule. I'm pointing down at this blue and red cartoon here, and on this end of the helium, I shouldn't be calling helium a molecule, but I am here. It's an atom, so excuse me. In any event, we have a partial positive charge on the right side of the helium atom. And so just for a split second, this helium atom looks polar just for that split second. It's not going to stay that way, so we call it a temporary dipole. If that happens in essentially the same split second, it's going to induce a change in the neighboring helium atom. So in column C, what we see is the electrons that were fairly evenly distributed in this helium atom are now repelled by these two electrons, which are being attracted to this helium nucleus. And so now for this same split second, we're assuming the electrons are moving faster than our camera, this helium atom now also has an unsymmetrical distribution of negative charge, and it has a partially positive and partially negative end. So we have a temporary induced dipole that formed because of this temporary dipole, and we say we now have some sort of temporary interaction between the partially negative end of one atom and the partially positive end of the other, and we say this fleeting attraction is the source of the dispersion forces in nonpolar molecules, in this case, nonpolar helium atoms. Dispersion forces will increase as electron clouds become more polarizable. So if you have more electrons and they're easier to push around, then that atom, or in most cases molecules, are more polarizable and more subject to larger and more significant dispersion forces. So we say dispersion forces generally increase as molecules become larger or have larger molar masses and more electrons. The dispersion forces between helium atoms that we just talked about, just to define what dispersion forces are really very weak. However, heavier noble gases, that would be other elements in the same column or period of the periodic table that are larger and have more polarizable electron clouds, have increasingly significant dispersion forces. Now let me illustrate. You'll notice at the top of the table we have helium. It has a very low molar mass, very low boiling point. Below helium in the periodic table is neon. Neon is larger, has a larger molar mass, more electrons, more polarizable electron clouds. It has a higher boiling point. If you go down all the way to xenon, the boiling point is now up to 165 K. Still pretty cold, but a lot hotter than 4.2 for helium. So what we see here is that as the molar masses of the noble gases increase, dispersion forces increase, and this is reflected by an increase in the boiling points of each of these substances. And we need to remind ourselves that boiling point is a measure of the strength of the intermolecular forces, since it scales, the boiling point does, with the energy needed to separate molecules, or atoms in this case, in the liquid in order to form a gas. So, take-home lesson here, we have 5 examples of atoms that are nonpolar, can only have dispersion forces, but the dispersion forces become larger as reflected in the larger boiling points as the molar masses increase. Another way of saying that are the electron clouds become larger and more polarizable. Recall from slide 2 that those 3 nonpolar molecules, chlorine, bromine, iodine, show increasingly larger intermolecular or dispersion forces specifically, and this is reflected in the fact that chlorine, the smallest and lightest in the series, exists as a gas at room temperature in 1 atmosphere of pressure, while the heavier and larger bromine exists as a liquid, and the heaviest and largest iodine exists as a solid. We can of course see the effects of the increasing dispersion forces reflected in other properties under conditions far from room temperature for these 3 molecules. So here's a table of data to consider. We know that dispersion forces are increasing as we go from chlorine to bromine to iodine. We've established that, and we can see this reflected in increasing boiling points of the liquid, in increasing melting points of the solids, and in increasing heats of vaporization of the liquid forms. So we'll restate that again right here. The increasing dispersion forces in this series are reflected in the fact that the melting points of the solid forms increase, the boiling points of the liquid forms increase, going from chlorine to bromine to iodine. The delta H of vaporization values, which remember is a measure of the energy needed to separate a mole of molecules in the liquid state to form a mole of molecules in the gaseous state, those increase, going from chlorine to bromine to iodine. You may be wondering why I threw in the bond energies here, XX bond energies. That would be the energy required to break the chlorine-chlorine bond, the bromine-bromine bond, or the iodine-iodine bond. Remember, the bond energies are a reflection of the intramolecular forces, and they are, in every case, larger than the delta H of vaporization values, which we said are a reflection of the intermolecular forces operating between the molecules. The effects of molecular size and molar mass on the magnitude of dispersion forces can also be seen in carbon-based molecules. For example, the graph below shows the increasing boiling points of a series of increasingly larger hydrocarbons. Hydrocarbons are compounds that contain only carbon and hydrogen. So here we have N-pentane, which contains 5 carbons and 12 hydrogens, and this little cartoon is a small space-filling model of this molecule. And the boiling point of N-pentane, which is the lightest in this series, is a little under 40 degrees C. But as the molecules contain more and more carbon and hydrogen, in other words, become larger and have larger molar masses, their boiling points increase all the way up to nonane, containing 9 carbons and 20 hydrogens. It has a boiling point of about 150 degrees. That's 50 degrees higher than the boiling point of water. So all of these are considered nonpolar molecules. That may not be immediately obvious, so we'll just tell you. So they all only have dispersion forces, but the dispersion forces, which increase with increasing molar mass, actually become quite significant and give octane and nonane fairly high boiling points. Even molecular shape can have an effect on the magnitude of dispersion forces between molecules. Consider, for example, the isomers N-pentane and neopentane shown to the right. Well, pentane has 5 carbons and neopentane has 5 carbons. Both have 12 hydrogens. That's why they're isomers. They have the same molecular formula. They're obviously different compounds. They're put together differently. For N-pentane, the carbon chain is kind of stretched out, even though it has this zigzag pattern. And so here we have 2 N-pentanes sitting next to each other. Above here, we have the 2 N-pentanes, their space-filling models sitting next to each other. Now you can criticize my model here because my space-filling model is not as long as my Lewis structure model. Can't do much about that without distorting this diagram horribly. The point here is that the shape of N-pentane is such that when 2 N-pentanes line up next to each other, there's a pretty big surface area of interaction between the two, so there's a large area for dispersion forces to operate. Neopentane, which again also contains 5 carbons and 12 hydrogens, is shaped entirely differently. It's shaped more spherically, and so when 2 neopentanes approach each other, there's not a lot of area for interaction by dispersion forces. So the result is the dispersion forces in N-pentane are significantly larger than the dispersion forces in neopentane. And it's not because N-pentane is any heavier. Its molar mass is exactly the same as the molar mass of neopentane. The difference between these boiling points, which is significant, 36.1 degrees versus 9.5, is simply because of the difference in molecular shape between the two isomers. So remember, dispersion forces operate between all molecules, not just in nonpolar molecules like those used in the last few examples. So going forward, when we talk about polar molecules, you can't forget about dispersion forces.